Hello, welcome to my course on the MOSFET. It covers the operation and dependence of physical parameters of MOSFET FETs. My name is Dr. John Aitken. I worked on the area of FETs for more years than I am comfortable telling you about with IBM when I was working. I'm now retired, and I'd be delighted to share what I know with you and about FETs. If you're looking for some printed material to help you through this as well, I recommend, there's quite a few of them out there. One of my favorites is one by Donald Neamen called Semiconductor Physics, and it is published by McGraw-Hill. But there are other ones out there that are also useful. Tower and Ning, Fundamentals of Modern VLSI Devices, printed by Cambridge University Press. Simon Z, Semiconductor Devices, Physics and Technology. Simon Z, VLSI Technology, that's also a very good introductory book. And Streetman, Solid State Electronic Devices by Prentice Hall, and Physics and Technology of Semiconductor Devices by Andrew Grove, published by Wiley. For those who are younger than I, you may not recognize the name Andrew Grove, but Andrew Grove is one of the founding fathers of Intel, and he knows FETs very well, as you might imagine. The content of the course is in broad outline is presented here. We'll cover the structure, function, physical principles, materials, and processing required to understand FET devices and parameters. We'll be covering the origin of charges and surface states from various sources and their impact on yield at T0 or reliability in the field. MOSFETs in your life. Every day you carry around or use devices with several billion MOSFETs. Your mobile phone, by the way, which is presented on the right, this happens to be an Apple, has about 10 billion transistors in it. Your computer at home has about the same number. Your TV has less, but they're serving a different function. In the mobile phone and computer, the transistors are used both to do logical operations and memory. Your TV is mostly a memory operation, and that's why there are fewer of the transistors in it. These transistors are very small. About 5,000 of them can fit across a human hair. This is a picture of the inside of your telephone. As you can see, there are lots of little black packages in there, and those black packages contain our chips, which contain MOSFETs, and they're mounted on green motherboards. If you were to take your computer apart, you would find a very similar kind of arrangement. What's a MOSFET? MOSFET is an abbreviation for a metal-oxide-semiconductor field effect transistor. Each one of those is describing something about the MOSFET. FET stands for field effect transistor. It refers to a transistor where an electric field applied at the gate opens a conducting channel between the source and drain contacts of the transistor, allowing mobile carriers to flow between them. It's most simply described probably as a switch that switches between two states where the contacts of the transistor are connected or disconnected. MOS refers to the metal oxide semiconductor gate structure, which acts to impress an electric field on the channel between the source and drain contacts. This is a very simple picture of a MOSFET, and I put a generic MOSFET on here because I'm talking about a MOSFET which can either be an NMOS or PMOS device, depending on the kind of substrate that it is built on. But the current flow in a MOSFET is turned off and on by the action of the gate voltage here on the silicon area underneath the gate. Voltages are applied to a source and a drain, and those voltages tend to make the current flow when the device is turned on between them. MOSFET-based technologies. MOSFETs are the most commonly used transistors and are used to make modern microelectronic integrated circuits, such as SRAM and DRAM memories, logic chips, microprocessors, RF and communication chips. They are advantageous because of their inherently low power consumption, high speed, and high density. CMOS, which is an abbreviation for complementary metal oxide semiconductor technology, provides the bulk of the integrated circuits made in the world today. CMOS is a technology that contains both NMOS and PMOS devices, and NMOS technology contains solely NMOS devices. But they have largely replaced bipolar technology in the past 20 years. Bipolar devices have some niche applications, including bi-CMOS circuits, but we won't discuss them here. We'll talk about NMOS technologies. Just to give you an idea of what these things look like, this is a picture of a semiconductor wafer, and on that semiconductor wafer you see patterns, shiny patterns of different colors. Those different colors represent different materials, and chips are fabricated in parallel on a 12-inch silicon wafer. There's about 400 chips on each wafer, and the wafer is diced into individual die and packaged to give you something like I showed you in the picture of the inside of your telephone. There are various types of chips on a wafer. Different circuit designs on each wafer are shown here. These are four or five different wafers presented there. Individual transistors are too small to be seen, as you can imagine, since 4,000 of them can fit on a human hair, but they are integral parts of each circuit on the chip. This is a picture of a diced and packaged memory chip that you might find inside your phone or computer. The gold and black areas are areas that either insulate or conduct electricity to contacts on the chip. The blue patterns on the inside are actual transistors or other circuit elements that are needed for the operation of the chip. And as I said earlier, these chips are mounted on a motherboard, that green thing there, that carries voltages and connects the chips. The individual, the chips are all connected through these metal wires to the devices on the inside of the chip and make it work.